In this lesson, we will continue to discuss parametric statistical inference. We will start by learning about hypothesis testing and its logic to make decisions about the population parameters we learned about in the last lesson. The null hypothesis represents the default assumption. It states that there is no relationship in the population and what we see is due to random chance. In a test of the impact of smoking and lung cancer, the null hypothesis is that smoking has no effect on whether or not a patient got lung cancer. The research hypothesis represents the alternative or experimental assumption. It states that there is a relationship in the population and not due to chance. Hypothesis testing can be compared to a case in our criminal justice system. In hypothesis testing, the null hypothesis is like a person being presumed innocent until proven guilty. Just like in court, the burden of proof rests on the researcher to provide evidence to reject the null hypothesis. Just as there is a risk in a courtroom of letting a guilty person go free, or convicting the innocent, there is a risk of coming to the wrong conclusion in statistics. One could be correct in two ways regarding your assessment of the null hypothesis: a true negative and a true positive result. You can also make two errors. A type 1 error is a false positive. This error occurs when the null hypothesis is incorrectly rejected, indicating a significant relationship, when, in reality, there is none. A type 2 error is a false negative. This error occurs when the null hypothesis is incorrectly not rejected, indicating no relationship when, in reality, there is one. The probability of committing a type 1 error is equal to the significance level set at the beginning. The probability of committing a type 2 error is denoted by beta and depends on factors such as sample size, effect size, and the chosen significance level. To control the type 1 error, we need to choose an appropriate significance level, typically denoted as alpha. Commonly used values for alpha are 0.05 or 5%. The specific alpha level establishes a critical region or critical value in the sampling distribution of the test statistic. This critical region defines the range of values that, if observed, would lead us to reject the null hypothesis, and we have statistical significance. So, we calculate a test statistic and a p-value. The probability value represents the probability of obtaining the observed sample data, or more extreme, assuming that the null hypothesis is true. That threshold alpha value at 0.05. If the p-value is smaller than 0.05, it tells us the observed data are unlikely to occur by chance alone. Then we reject the null hypothesis in favor of the alternative hypothesis. The smaller the p-value, the stronger the evidence against the null hypothesis. Where did we get the 5% from? The use of a 5% significance level is a convention that has been followed by statisticians for decades. 0.05 is the working convention. The probability of committing a type 2 error, a false negative, is denoted by beta, and depends on factors such as sample size, effect size, and the chosen significance level. Beta is directly related to the power of a statistical test. Power is the probability of correctly rejecting the null hypothesis when it is false, or the ability of a test to detect a true effect or relationship. Power is influenced by factors such as the sample size, the effect size, the magnitude of the true effect, the alpha, and the variability in the data. As power increases, the probability of committing a type 2 error decreases. Increasing the n's in a data set is the easiest way to do this. Computer software can calculate power, and the power of a test can be read from a reference table as well. Researchers use sample data to calculate a test statistic, which is then compared to a critical region on a theoretical distribution to make inferences about the population parameters. The one-sample t-test is a statistical test used to determine whether the mean of a single sample is significantly different from a hypothesized population mean. It is particularly useful when the population standard deviation is unknown, and the sample size is relatively small. The t-test is a statistical test that was developed by William C. Lee Gosset, a biochemist and statistician who worked for the Guinness Brewery in Dublin, Ireland, in the early 20th century. Gosset convinced the health department to accept his theory of sampling and analyzing the data in a new distribution to save tapping every keg for inspection. Due to company policy, Gosset published his work under the pseudonym Student, which is why the test is sometimes referred to as student's t-test. Let's do an example of a simple one-sample t-test with this data. To calculate the t-test statistic, we can use the following formula. T equals the sample mean minus the hypothesized population mean, 75 in this case, divided by the standard error of the mean, SEM. Recall that SEM is just the sample standard deviation divided by the square root of n. We can plug these values into the formula to calculate the t-test statistic. The result is that t equals -1.33. In order to interpret the t-test statistic and draw conclusions, we would need to compare it to a critical value. Where do we find the critical value? In the t-distribution table. Page 3 of our Charts and Tables Guide. With an n of 100, we are beyond the 60 degrees of freedom, at a critical value of 2.00. Since the absolute value of calculated test statistic is 1.33 and not greater than the critical value, our result is not significant, and we have no evidence to reject the null hypothesis here. We can have StatCrunch do the calculations too. Just click on the Stat tab, then T-stats, then one sample, then with summary and plug in the numbers. Be sure to put in the population mean that you are comparing the sample mean to, 75 in this case, as the default is 0. Click Compute and StatCrunch will calculate the test statistic, give you the hypotheses it tested, and a p-value. The p-value is above 0.05 here, further confirming our result is not significant. Statistical significance is a measure of how likely the observed result would occur if the null hypothesis were true. If the null hypothesis is rejected, this indicates that there is a significant finding in the data that supports the alternative hypothesis. On the other hand, when the null hypothesis is not rejected, it means that there is insufficient evidence to conclude that the observed result is statistically different from what would be expected by chance alone. Statistical significance does not directly imply the importance or clinical meaning of a result. It simply addresses the likelihood of observing a particular result. Two-tailed statistical tests are commonly used in hypothesis testing when there is no specific directional hypothesis or when we want to detect the possibility of a difference in either direction. Put simply, we don't know if the data points in our sample will be above or below the mean. A drug may help a subject's condition, or it may make it worse. We have to look at both sides of the theoretical t-distribution. A one-tailed test, also known as a one-sided test, is used when prior knowledge provides a specific directional hypothesis. In such cases, researchers are interested in determining if the observed data supports the hypothesis in one particular direction. Statistical tests often rely on certain assumptions about the data being analyzed. These assumptions ensure that the test is valid and produces reliable results. The t-test is also based on certain assumptions, and violating these assumptions can affect the validity of the test results. Parametric tests are statistical tests that make assumptions about the distribution of the data being analyzed. These tests are widely used in research and data analysis due to their various advantages. Non-parametric statistical tests are used when the assumptions of parametric tests are not met or when dealing with data that does not follow a specific distribution. In summary, non-parametric tests are easier to compute and are more flexible. Parametric tests generally have higher power when the assumptions are met. The choice between parametric and non-parametric tests should be based on the specific characteristics of the data and the research question at hand. Degrees of freedom refers to the number of values in a sample that are free to vary after certain restrictions or conditions are imposed on the data. In statistical testing, degrees of freedom are crucial because they determine the critical values and the shape of the sampling distribution of the test statistic. For a one-sample t-test, the degrees of freedom are simply n-1. The steps involved in hypothesis testing are summarized here. We calculate the test statistic and compare that value to the tabled critical value to determine significance. And we can follow a similar logic for when we analyze the data by computer software. The actual p-value can be calculated by StatCrunch, and we can determine significance and the fate of the null hypothesis from that result as well as the test statistic that is calculated for us. Let's do an example using data from a study of inorganic phosphorus levels. Here our null hypothesis is that the phosphorus levels of the people in our study are equal to the national average of 1.2. To run the one-sample test, enter or load the data into StatCrunch. Click on the Stat tab, then T-Stats, then one sample, then with data as we have all the individual data here, right? Select the phosphorus levels variable, and be sure to put in the population mean that you are comparing the sample mean to, 1.2 in this case, as the default is 0. Click Compute and StatCrunch will calculate the test statistic, give you the hypotheses it tested, and a p-value. The p-value is above 0.05 here, 0.13, confirming our result is not significant. Here is our degrees of freedom, which is n-1, right? We have 12 people in our study, and 12 minus 1 is 11. Here's the calculated t-stat, and our p-value of 0.13. If we look at the test statistic in the chart, back to our table, and we take the absolute value of the test statistic with 11 degrees of freedom, our critical value is 2.2. The absolute value of our test statistic is not greater than 2.2, and this also tells us it's not a significant result. For the confidence intervals, we can click on Options and Edit. And then we can click on the confidence intervals in the Perform area. This is defaulted to 95%. Compute and StatCrunch prints them out. Our lower limit is 1.032 and our upper limit is 1.225. What does this mean? If we keep sampling people's phosphorus levels, our values 95 times out of 100 will be between 1.032 and 1.225. We can do another example with a much larger data set looking at hospital readmission rates in the state of Texas. Once the data is loaded into StatCrunch, to run the one-sample test, click on the Stat tab, then T-Stats, then one sample, then with data as we have all the individual data here, right? Select the readmission rate and enter the population value, and click Compute. This one is significant because the p-value is below 0.05. We then can look at the critical t-value in the table at 108 degrees of freedom. We are at 1.98, and the absolute value of our test statistic is greater than our cutoff value, again showing it's significant. We can then go back and find the confidence intervals here. Hypothesis testing is a fundamental statistical technique that involves making decisions about population parameters based on sample data. In the next lesson, we will learn even more parametric sample data tests.